Welcome to Hot Chips 31. Session 4, ML Training.
I'll say I'm super psyched about this session. I feel like over the last few years, we've had a huge number of great discussions and employments, particularly focusing on the inference side. But I think the training part of the machine learning puzzle has not gotten as much love. And finally, at this session, we're fixing that. Training is a bunch harder than inference. There are much tougher memory requirements, much longer lifetime requirements, huge flops to deploy. And I think this year, as you'll see from the session and the presentations we're about to see, is poised to be the breakout year where the startups that were founded finally come to market and show us what they can do in the training space compared to what's been possible previously with CPUs, GPUs, and TPUs. I think you'll see as part of this talk that there's been some really interesting convergent or parallel evolution in the training space. There's a lot of designs that look to me like there's a large compute-intensive die which might use systolic arrays, a bunch of HBM stack integration in 2.5D format, and pretty aggressive interconnect technologies. A lot of people seem to have come to a very similar engineering point. And so I might encourage you to think about, not the similarities, but what's different about each of the solutions that we see, including one which is incredibly wild and I'm hoping will blow all of your minds. For the first talk today, we have a slightly unusual format. We're going to show a video that was taped earlier by our presenter, and then we'll have a Q&A session over video conference from China, as it turns out. Our speaker is Dr. Heng Liao, who is a Huawei fellow, the chief scientist of the 2012 labs at Huawei, the chief scientist at HiSilicon, and he directly leads DaVinci hardware and software efforts, which he's going to tell us about right now.
Thank you. It's a great honor to be here on behalf of the DaVinci team. I'm here to, through this video, I'm here to share with you the design thinkings behind the scalable architecture for neural network computing. Recent advancements in AI technologies bring great promise in creating intelligent devices for a wide range of applications, ranging from very small wearable and IoT devices to smartphones, to intelligent robots, to autonomous vehicles, and also large data center devices. Having the right computing architecture is the key enabling factor for AI deployment in such wide scale. When we set out to create a new AI computing architecture, we struggle between the choice of creating a narrowly focused solution for a given performance range, or we try to create a unified architecture that can cover a wide spectrum. We chose the latter approach because there's significant software ecosystem cost in supporting a new computing architecture. When we look at the requirement on individual chips, we find that there's approximately 6 order of magnitude in performance difference. And based on this architecture, we created a family of DaVinci cores from DaVinci Tiny, Little, Mini, and also the DaVinci Max cores. The performance of each core varies greatly. At the chip level, we also put in a different number of these cores in order to further increase the scalability of our solutions. Based on our history, there's already a great variety of heterogeneous computing architectures ranging from CPU, GPU, DSPs, and video processors of various kinds. When we look at these computing architectures, we find that they represent a different trade-off points in the performance, power, and area space. And for DaVinci, optimize the computing architecture based on deep neural network algorithms. Here's some architecture details. DaVinci is a heterogeneous architecture based on a combination of three variety of computing units. We have the classical 1D scalar units, which is more or less superscalar style RISC processor. We complement that with a rich and improved 2D matrix unit in order to perform the necessary activation functions and intermediate layers for neural networks. But most importantly, we have introduced the very large 3D matrix unit in order to provide high intensity computing horsepower. So the table below illustrates the benefit of having a 3D computing architecture. One can see that when the width of the cube is 16, the cube unit is able to perform 4,000 n cube number of multiply and accumulation operations. So that's 4,096 multiplication and 4,096 accumulation functions. In total, it has an intrinsic parallelism of 8,000. We also find that the cube unit brings great area and power benefits as illustrated on the table on the right-hand side. So when we put these variety of 1D, 2D, and 3D execution units together, we also surround them with explicit memory hierarchy design in order to provide matching memory bandwidth and a suitable hierarchy of memory such that the memory bandwidth demand can be gradually reduced as the traffic leaves the core. So some of the key building blocks includes the cube unit, the vector unit, and also the scalar unit. But there's also the MTE unit, which manages the memory transfer across the different components, different variety of buffers. When we look at the variety of buffers, we have the L0 buffers providing operands and result storage space, the unified buffer providing the operating space for the vector operations. We also have a L1 buffer which provides the space to reuse data that's frequently cycled through the execution pipelines. So as I mentioned earlier, there's many versions of the DaVinci Core ranging from tiny to the max. The different core configurations basically provides a range of resources in each component in this unified architecture. For example, the tiny version of the DaVinci Core has 512 MAC units within the cube, and the max version has over 8,000 MAC elements in the cube unit. But one of the key challenge is in balancing the right amount of resource in each portion of the design. So this table shows the key trade-off points or most important architecture design parameters, including the size of the cube unit, the operations within the vector units, and the width of L0, L1, and L2 bus and memory. So these numbers are chosen based on very intricate design considerations and profiling of a large variety of neural networks. For example, we have to balance the width of the vector unit and the number of MAC elements within the cube. So when we profile the resource requirements using different neural networks, we find that the ratio between the vector unit and the cube unit varies greatly from layer to layer and also from network to network. So when we choose the size of these units, we have to ensure that the most critical resource, being the cube unit utilization, is maximized rather than being blocked by insufficient resources in the vector unit, for example. And these curves shows that the cycle consumed by the cube unit versus the cycle consumed by the vector unit. So based on the design choices I showed in the table earlier, we can see that this design choice can satisfy the requirement that the cube unit is never blocked by the vector, because most of the time, almost across different layers, with the exception of the beginning layer of ResNet 50 and MobileNet, most of the time the cycle consumed by the cube unit is much greater than the cycle consumed by the vector unit. Therefore, the execution time of the vector can be hidden by the execution time of the cube. And similarly, we did the profiling on the level 1 memory bandwidth. This curve shows that as long as the bus on L1 memory is over approximately 2000, we can provide sufficient bandwidth to sustain the pipeline operation without introducing stalls. So once I have optimized core hardware design, there's a significant challenge in creating the developer stack for such a domain-specific architecture. Starting from the instruction set, we introduce a C-level programming interface, which we call CCEC. But this level, the programmers are exposed to all architecture details, and therefore the high-performance library can be written by experts who has architecture knowledge. We also introduce what we call the level 2 compiler, or the TIC interface, which I will explain further later on. At this level, we provide the ability for the programmer to represent parallelism in the source code. When we move up further to provide architecture independent programming layer, that brought us to level 3, which can be written by people who has no knowledge about hardware. And at this level, we need to have advanced compiler technique such that the mapping from a mathematical representation of the program semantics can be done automatically by the tools, yet creating optimized code for the given hardware. So one of the big challenge in programming the DaVinci architecture is due to the fact that the hardware has internal parallelism. So inside the DaVinci Core, we have 4 parallel execution pipelines: the scalar, the memory transfer unit pipeline, the vector pipeline, and the cube pipeline. These pipelines at the execution stage were loosely coupled. Parallel operations can be executed by these 4 pipelines at the same time. However, the processor only provides a single thread support. There's a significant challenge in representing parallelism using a single thread of instruction flow. One obvious solution is to introduce hardware multi-thread. So suppose we have 2 or 4 threads, each representing a sequence of sequential operations. These threads can be scheduled and dispatched into the parallel execution pipelines. Although this will address the difficulty in programming parallelism, but there's also significant hardware cost that comes along with the hardware multi-threading. Instead of introducing hardware multi-threading, we try to utilize or implement the idea of multi-threading using software compiler techniques. This is due to the fact that a lot of the low-level neural network codes are written typically in the form of deeply nested loops. And we also find that in many cases, the different iterations of the same loop body are independent from each other. So we can mark a certain loop body or what we call iterator kernel to be independent and to be a candidate for multi-thread. And the compiler can automatically expand the loop body into several threads and do the scheduling across multiple iterations. So this diagram shows the concept. So one can see that in a single thread representation, the loop body is executed sequentially in iterations 1 through m. But when we do software multi-threading in the TIC layer of programming, we expand the loop body into 2 copies and then do the scheduling so that iteration 1, 2 can be executed and scheduled at the same time. And similarly, 3, 4, and 5, 6 are also scheduled in parallel. Therefore, this addresses the difficulty in utilizing the parallel pipeline in the hardware. But for level 3 programming, this is require a very advanced compiler technique which converts program representation from architecture-independent domain-specific language to the C level and then to the binary level. And one can see that this is a multi-stage lowering process, and there's many millions of legitimate mapping from the higher level representation to the lower level. And we actually also have developed the advanced compiler utilizing reinforcement learning technique to search the mapping space in order to find the optimal schedule and tiling strategy for a given program. So when we put all these together, we have the many DaVinci cores in the hardware and task scheduler level, and going up to the CAN layer, which is architecture-dependent layer that provides operator library function. And we have the graph engine layer, which provides architecture-independent graph optimization function. And on top of that, we have the familiar AI frameworks that programmers are familiar with, such as TensorFlow, PyTorch. We also have created our own version of an AI framework, MindSport. So once we have the DaVinci cores, we created a great variety of SoCs, including a mobile application processor SoC, the NPU being the most computation-intensive portion of the mobile AP nowadays. We also created automotive SoC for ADAS applications, and AI inference SoC for cloud and edge computing devices, and also the Ascend910, which is AI training SoC, providing the class-leading compute horsepower for training applications. We even introduced the DaVinci Core in wireless base station SoCs to do real-time channel optimization for base stations. One of the major challenges that we encounter in the DaVinci chipset is the memory wall issue. From this table, one can see that the Ascend910 device at the core of the compute units demands memory bandwidth of 2048 terabyte per second throughput. However, even with the most advanced HBM technology, we were only able to provide just over 1 terabyte per second of raw throughput. There's over 2,000 times gap between the raw memory throughput required and versus what can be supported by the memory subsystem. How do we overcome this wide gap in memory bandwidth? We address this by multi-layer memory hierarchy. At layer 0, we have to provide matching bandwidth to the execution unit. But as we move down the hierarchy, each layer, we try to reduce the memory bandwidth by a factor of approximately 10. So this is heavily rely on the fact that there's memory reuse at each layer of the hierarchy. Apart from architectural innovations, we also try to embrace 3D IC technology in order to address the challenges in memory wall, but also I/O wall and logic wall. By using 3D stacking technique, we can increase the total amount and bandwidth of memory that can be attached, tightly attached to the logic. But also we could increase the usable die size and also utilize heterogeneous process node for the I/O interfaces. For the next generation, this picture shows that we are, on the one hand, try to use advanced technique to provide more HBM bandwidth off chip, but also use 3D SRAM technique to increase the total amount of on-chip buffer space. And similarly, in the mobile AP space, we face a similar memory wall issue, but at a smaller scale. To address that memory wall issue, we use custom design wide I/O DRAM that's 3D bonded on top of the AP, but also utilize a multi-layer logic die to increase the usable die size. So here's some detailed numbers about the Ascend family. The most notable one is the Ascend910, which has 256 teraflops in FP16 compute horsepower, but also 512 teraops of int-A compute horsepower. It also includes 128 channels of full HD video decoder, so that video data can be decoded on chip and processed without leaving the device. And the total power is 350 watts, and it's manufactured in 7+ EUV process. So when we compare Ascend910 versus other leading devices on the market, we find that the architecture innovations does bring increase some advantage in the compute density. So at the moment, it seems to be the class leading device. And we have put 8 of these devices together in a single server design. And this design has 8 Ascend910 chips, and it consumes about 6,000 watts. of power. And we also put 2048 nodes together to create a Ascend910 cluster. The combined compute horsepower is 512 petaflops in FP16. So here's a die shot of the Ascend910. So as what you can see, this is a rather complicated package with the compute die, 456 millimeter square compute die in the middle. It also has a Nimbus, which is the I/O die, and 4 HBM stacks on the side. The Ascend910 floor plan, so you can see that there's total of 32 DaVinci cores combined together. The physical device provides 128 gigabyte per second of read bandwidth and 120 gigabyte per second of write bandwidth per core. On the device, it also provides 3 ports of 240 gigabit per second chip-to-chip ports for NUMA connections, and also 2 100 gig Rocky interface for networking. The network on chip is arranged in a mesh fashion, 6 rows and 4 columns, and the network on chip provides total of 4 terabyte per second access bandwidth to the L2 memory hierarchy, and also 1.2 terabyte per second of bandwidth to off-chip HBM subsystem. Here's a die shot of the smaller version, Ascend310. And finally, the package devices. The DaVinci project was a super exciting project. From concept to sample back, the first generation DaVinci only took 11 months. Many of my colleagues have spent endless hours making this happen. I will take this opportunity to acknowledge their great contribution. This year, it's estimated that we will deploy over 100 million devices with DaVinci Core inside. I will take this opportunity to answer questions from the audience now. Thank you.
So as before, there are microphones. Please come up. And when you're asking questions, may I ask you to please be respectful of the speed of light delay to China and also transmission delays in transcribing what you're saying to Dr. Liao. And if people aren't going to ask questions, I'll ask. Dr. Liao, if you can hear us, can you comment more about the 3D stacking SRAM technologies that you are planning to incorporate either in this generation or the next generation? It seems like that is quite a different direction from what we've seen in many other chips that are deployed in the space.
Sorry, yeah, can you repeat the question? The sound was cutting out.
Okay, one more time on the question. For the die-stacked 3D SRAMs that you're considering either for your first or second generation, can you tell us about some of the technical concerns as far as doing the stacking, cooling the compute chips, and the density that you can get with that kind of SRAM?
So die stacking, yes. For stacking SRAM, I think the major concern was providing the power to the chip and also the thermal issues that arises from the stacked die. But from analysis that we have done, I think at about 3 to 400 to 500 watt range, I think these issues can be resolved. The bigger challenge comes with stacking DRAM die because not only the thinning process will compromise the DRAM retention time, but also DRAM is much more sensitive to has a much tighter thermal budget to deal with.
Cool. Audience question?
Hello, Mr. Liao. Can you hear me?
Yes.
Hi, my name is Gary Brown. I'm from Intel. I want to first say I really appreciate that you were able to present here at this forum. It's been an international conference for many years, and I'm really glad you got to give a really nice presentation, so thank you.
Oh, thank you, Gary.
I'm very curious. And it was an excellent presentation. I'm very curious. So 350 teraflops, fantastic number. And I was curious to ask, were you planning on presenting at some point the actual efficiency that you're getting with real benchmarks? And would you be also interested in participating in such benchmark consortia that we've been hearing about today, such as MLPerf?
Oh, yes, indeed. Well, not only we will present the real benchmark data for individual chip level, but we are also working on preparing the data for presenting the benchmark for the large cluster of 2,048 nodes that we have constructed. So indeed, we will participate in MLPerf activity shortly. Just stay tuned for the announcements that will be coming in this month, also in the coming quarter.
Thank you very much.
Oh, yes, this is Brian Holden, Can Do Bus. Good to talk to you again, Heng, after so many years. In the evolution of HBM, there's been proposals to do HBM3 at a higher rate, but a much shorter reach, which would break the double stack on each side of the processor. Would you, how would you interpret the trade-off between reach and bandwidth on HBM?
Well, I think the reach for HBM roadmap, I think the reach it's indeed a major issue, because if you shorten the reach, you have to put the DRAM on top of the logic die, and this creates a serious thermal budget issue.
Yeah, right.
So I think first of all, the HBM itself at the moment utilizes a relatively low density interconnect, basically TC thermal compression bonding technique. So our belief is that the bonding technique need to be improved, and also the density of wiring at the vertical direction need to be increased, and also this will create the opportunity to significantly reduce the power. But in terms of connecting the HDBM stack to the main logic die, I think at the moment it seems like putting HBM on the side is still the more practical approach.
Yeah.
But we will try both, putting it both on the side, but also finding ways to stack it on top.
Great, thanks.
If you'll forgive me as session chair, I think I'm going to lean into the time a little bit for the next few presentations, because we don't have a chance to talk to Dr. Liao in the hallway outside after this. And so why don't we take the one last audience question, and we'll attempt to catch up in the air.
Thank you. Thank you, Dr. Liao, for the excellent talk. My question here is, do you see a clear migration path, a migration of the technology from from data center to the edge, and to make this device available for edge computing?
Sorry, I didn't really quite catch the question. Cliff, can you help repeat the question?
I think the question was about, do we think one architecture can serve both data center and edge needs to serve a variety of different deployment packages, which I think was partially in your slides.
Sorry, I didn't quite get that.
Well, in light of the Internet of Things, would you see a technology migration path from the data center side to the edge for this device or for this architecture?
Oh, yes, actually, one of the major emphasis of the architecture design is to make it highly scalable. We actually have not only utilize it in edge, but also in client devices such as cell phones and smart cameras, and also utilize the same architecture in the data center. And this, the reason we make that choice is because we realize creating the software stack for this architecture is a tremendous effort. So we want to cross-leverage the same software stack, same architecture compatibility across very small devices and very large devices. Yes, we actually have utilized it both for the edge and the data center.
Awesome. What about the power consumption for this device?
I think I'd better cut you off there on the basis of time. So thank you, Dr. Liao, for a wonderful presentation and for answering our questions. I was disappointed to hear that our second speaker, whose name is Andrew Yang, is not actually the presidential candidate Andrew Yang. He is, however, a senior principal engineer at Intel. He is the lead of their training product architecture in the AI products group. He joined Intel in 2016 as part of the Nirvana acquisition, so I think he has seen both startup culture and big company culture, and he's going to tell us about Spring Crest machines.
Right. Thanks to Cliff for that introduction. And today I'll be disclosing the Spring Crest Deep Learning Accelerator architecture. Spring Crest is part of Intel's Nirvana NNP-T line of deep learning accelerators. Our legal team is earning their paycheck. So what should we consider when we're architecting a device to excel at deep learning training? Time to train and power efficiency are two key metrics. So the faster you train, the faster you can integrate new data and deploy new models, as well as experiment with new topologies. Utilization, as well as scale out across multiple nodes, drive faster training time. And as important as it is to train quickly, it's also equally important to train efficiently. When you're training models across thousands of nodes, that can take weeks of time. So efficient use of your allocated power directly impacts your cost to train. So the trend we see in DNNs is that state-of-the-art model sizes have been growing at an exponential rate for the past 6 years, and they're continuing to grow this way in the future. And as model sizes continue to get larger, what that means is you need more compute, more memory bandwidth, as well as more memory capacity to store your model parameters as well as activations. And when we look at the DNNs themselves, they have been and they continue to be dominated by GEMMs and convolutions for the majority of math operations that are involved. And what this means for a deep learning training accelerator is that there's a few things that the architecture needs to focus on. So power efficiency and high utilization are key in order to train the model as fast as possible within a limited power budget. You need to fill the die with as much compute as your power will allow, as well as support programmability in order to cover non-GEMM operations. And you really need to focus on the memory communication to feed the available compute, because compute problems rapidly become data movement problems if it's not architected properly. From a hardware point of view, deep learning is at least as much of a communication problem as it is a data problem, a compute problem. And finally, you need a very clear scale-out strategy to support multiple nodes in order to enable larger models and faster training time. So given these key metrics for training, how did that drive the architecture of Spring Crest? We want to train a network as fast as possible within a given power budget, and we want to support large state-of-the-art models and data sets because that's the industry trend. So we need to focus on real-world utilization instead of just peak tops, where utilization is your percentage of peak tops that you can actually achieve while running a workload. All the multipliers in the world don't really matter if you can't keep them fed. So you need to look at the die area that's allocated between the max, the local and on-die memory, as well as communication in order to create a device with both a large amount of compute, but the compute that you can keep fed on data sizes both large and small. With GEMMs and convolutions, the goal is to be compute-bound on all but the smallest of problem sizes. Whereas with vector and scalar operations, you want to be memory-bound. And to keep both keep the compute fed, as well as maximize power efficiency, you need to keep data local and reuse it as much as possible. We focused on a built-in scale-out support from both a hardware and software point of view. We have a consistent programming model on-die and off-die to enable both data as well as model parallelism. And finally, deep learning algorithms are changing rapidly. So you need to enable a degree of flexibility and programmability in order to support future workloads. The fact of the matter is that the workloads of today are not the workloads of tomorrow. So this is a block diagram of the Crest NNP-T SoC. Starting from the outside in, Crest includes 4 stacks of HBM2 memory integrated in a 2.5D packaging technology. As an accelerator, it communicates with the host CPU via PCIe Gen 4 by 16. The core of the chip is consumed by 24 tensor processors, which we call TPCs. These TPCs provide 60 megabytes of on-chip memory and up to 119 TOPS of bfloat compute. We also integrate 64 SerDes lanes to enable direct communication between Crest chips, either through backplane or cables. Crest is implemented on TSMC's 16-nanometer process with a die size of 680 square millimeters and a 1,200 square millimeter interposer that contains both the SoC die as well as the 4 stacks of HBM memory. These 4 HBM memory stacks support up to 32 gigabytes of memory capacity. The Crest core operates at up to 1.1 gigahertz, and that's combined with HBM 2400 memory speeds. The scale-out SerDes links operate at 28 gigabits per second per lane, and they're grouped into quads of 112 gigabits for a total aggregate bandwidth of 3.6 terabits per second between chips. The main die and HBM are all contained on a 60 by 60 millimeter package that supports both PCIe as well as OEM card form factors. Let's talk a bit about software. So NNP-T will support a variety of frameworks, initially starting with TensorFlow and PaddlePaddle, and adding others as they're developed. We enable support for multiple frameworks by interfacing with ngraph, which is our deep learning graph compiler. So ngraph is open source, and it provides a common set of performance optimizations, such as operation fusing and support for multiple tensor layouts, while providing a clean interface to our Crest DNN and kernel libraries. So the benefit to the user is that they can rely on Intel to provide the low-level kernel optimizations for performance, while ngraph allows us to decouple these optimizations from the framework. So the data scientist is free to use the framework of their choice. NNP-T has a tensor-based ISA that's both flexible and programmable, yet with a limited instruction set to operations required for deep learning in order to reduce overhead and improve efficiency. The ISA is also extensible through custom microcontroller instructions. The goal is to provide support for all future deep learning workloads without burdening the ISA with that of a fully general-purpose processor. Within the ISA, all operands are treated as tensor, and there's support for a lot of native tensor operations that are used by data scientists, such as transpose and tensor slicing, in addition to your typical compute operations. The distributed programming model that we use is hierarchical and consistent both on-chip and off-chip. So large problems are mapped to multiple TPCs on the die, and that scales to multi-die in the same manner as the problem size grows. The synchronization as well as the communication primitives are consistent both on-die and off-die. So you can apply hierarchical algorithms to partition the problem at the level of a TPC, an SoC or hundreds of nodes working together. In order to allow for the best utilization, hardware memory management is kept to a minimum to avoid interfering with software optimizations. So message passing, memory allocation, and management are fully under software control in order to allow full optimization of both data locality as well as data residency. Ultimately, NNP-T provides a simple, scalable, and extensible ISA that makes it easy for software to perform direct hardware optimization, as well as scale out in a hierarchical manner. So this is a block diagram of the TPC, or the Tensor Processing Cluster, and it's the heart of Crest with 24 instances on the SoC. And there's 4 major subsystems to the TPC that I'll be getting into more details on. In the green box, we have our on-chip router, which passes data both directly between the TPCs as well as provides communication to shared peripherals like PCI Express and the scale-out links. The yellow block is the control path, and that plays the role of decoding, scheduling, and retiring instructions, as well as coordinating the compute and memory blocks within the TPC. There's 2 of the red blocks, which are the compute blocks within the TPC, and that block contains a large matrix multiply array, as well as a variety of vector operations, as well as specialized deep learning functions. The last block is the blue block, and that contains several local memory blocks that source and sync the data to the compute, as well as to the routing mesh. Multiple banks are used to provide high bandwidth. Also contained with the memory is a data transformation engine that we use to reformat data for convolutions, as well as other more general uses, such as tensor reshape. So state-of-the-art training accuracy used to require FP32, but the industry has been moving to lower precision numerics to improve both power and performance. Crest uses bfloat 16 with FP32 accumulation in its matrix multiply array. And when you compare bfloat 16 to other numeric formats, bfloat 16 kind of gives you the best of both worlds. You get the power efficiency and throughput of a 16-bit format, but you get the convergence and accuracy of single precision. So oftentimes the network needs little or no modification aside from conversion from single precision to bfloat 16. If you're more interested in more details on bfloat 16, I've cited a joint paper by Facebook and Intel in the footnotes. So the TPC compute block contains a 32 by 32 matrix multiply core using bfloat accumulating at FP32. 32 by 32 gives a good balance of data reuse to reduce power and memory bandwidth requirements, while not being so large that you lose a lot of performance due to quantization effects. In order to further reduce memory access as well as power, a partial product memory accumulates partial products within the compute block. Outside of the matrix multiply core, both FP32 and bfloat 16 operations are supported throughout a compound vector pipeline. This compound pipeline allows multiple operations to be performed on a set of inputs and intermediate values, which again reduces memory pressure and power. And supporting bfloat 16 in the vector pipeline allows for optimizations of non-GEMM operations based on the network accuracy requirements, which again can improve your overall performance and reduce training time. We include deep learning specific optimizations for things like activation functions, random number generation, reductions, and accumulations. Deep learning workloads generally rely very heavily on the memory to keep them fed. So Crest includes 4 stacks of HBM2 2400 memory to provide maximum off-chip memory bandwidth. On the chip, there's 2.5 megabytes of local memory per TPC for a total of 60 megabytes of distributed on-chip memory. This memory is highly banked and ported for simultaneous read and write access, and it also provides a native tensor transpose operation. So tensor transpose can be accomplished both reading and writing into memory without any additional overhead. And as I mentioned before, Crest provides software the flexibility to directly manage both data locality and data residency within both on-chip and HBM memory. So software can transfer data directly from the memory of one TPC to the memory of another rather than going back to HBM. This, again, minimizes your data movement off chip and puts data where it's needed for the compute. Spring Crest has a two-dimensional mesh architecture to enable communication and data transfer, both to memory and peripherals, as well as directly between the TPCs. We prioritize throughput over latency, as keeping the compute fed is generally a greater problem than your initial data latency. Spring Crest has independent buses for different traffic types to enable data to be transferred to HBM as well as the SerDes, while also simultaneously sending data directly between the TPCs without any interference between the traffic. And this data transfer is key to keeping data local and avoiding unnecessary transfer of data to and from HBM. So you can read data from HBM once and then directly transfer it among the TPCs to achieve high utilization and power efficiency. Software has full control of sending data both from local TPC memory, both to other TPCs, as well as directly over the SerDes links to reduce latency and HBM memory pressure. We talked earlier about how model sizes are increasing. So neural network model sizes are still increasing today, which means memory footprint as well as training time are bottlenecks. Spring Crest enables the user to interconnect hundreds of nodes together to make many chips look like one large system with a consistent programming model. The fact is, we don't want training time and model capacity to be customer bottlenecks. It's key to enable fast turnaround on new data and to enable model experimentation by the data scientist. To effectively enable model and data parallel training, Spring Crest has 16 quads of SerDes for 112 gigabits per second per quad to interconnect the chips together. The link architecture has a built-in programmable router that enables a variety of different glueless topologies, including but not limited to topologies such as a hybrid cube mesh, ring topology, or fully connected. The link architecture also supports multiple virtual channels and priorities to help avoid deadlock and provide additional flexibility for routing topologies. The links have a built-in reliable transport mechanism and support for direct transfer of data to local memory. So this scale-out architecture, combined with data transfers directly from on-die memory, results in very low latency and reduced HBM memory pressure, in addition to efficient transport of messages, both large and small. I'll be sharing a few micro benchmarks that demonstrate high utilization on real-world workloads and data sizes, and the ability to efficiently scale out performance via both data and model parallelism. So first, we'll look at GEMMs. So it's important to benchmark GEMM across a variety of sizes, because the fact of the matter is most architectures will do well on large square GEMMs because they're highly compute-bound. But in reality, deep learning training requires a variety of aspect ratios. Depending on the network itself or your phase of training, you can run into all sorts of different matrix sizes and aspect ratios. These numbers in the table, they might not look extremely high. And we certainly have a large number of GEM sizes where we can achieve 90+% utilization. But these sizes were chosen in particular because they've been shown to be challenging on other architectures as well. So on these sizes, we see roughly 2x better utilization than published results on competitive products. And similar to GEM, you need to benchmark convolutions across a variety of input dimensions and sizes, as well as number of filters and filter sizes, in order to see how it performs. You can see in the chart and the graph, which display the same data, we're able to achieve high utilization of the compute elements on a variety of sizes. These particular numbers are for FPROP, but we see similar utilization on both BPROP and update as well. The way we achieve this is Spring Crest has a convolution engine that transforms the data to keep compute fed, as well as reuse the data as much as possible. We also support multiple different data formats and tensor layouts, as well as parameter splitting to achieve the best efficiency depending on the network as well as the characteristics of the particular layer. The last benchmark I'll discuss today is related to communication. And I'll talk about the communication collectives a little bit. So this particular benchmark was collected on the system shown in the right. So there's 32 chips interconnected here. If you look at the picture, each of these yellow boxes is a chassis, and there's 8 cards in that chassis. And there's 4 of these chassis in a rack for a total of 32. Within the chassis, the cards are connected together in a ring topology. And between the chassis, we're also connected in a ring topology for this particular benchmark. So the first benchmark kind of sets our roof line. So it's a 2-card send and receive. So we have 2 cards that are interconnected together, and we want to see how much bandwidth can we achieve between the 2. And we're getting 161 gigabytes per second right now. And this is interesting as your roof line. So this is real data being sent between 2 cards, and it includes all your real-world inefficiencies, right? It includes your packet overhead, it includes your overhead for reliable transmission, scheduling inefficiencies, and that's what we achieve. Now, the more interesting thing is, okay, if that's your roof line, what are you achieving on real collectives? So there's 2 collectives that I want to talk about. The first is all reduce and broadcast. And so keep in mind, this is a real all reduce collective being performed on all 32 chips. And so that includes, scheduling your data to send it out, receiving it, doing reductions, and potentially sending and receiving more data. And we were able to achieve 151 gigabytes per second on the all reduce collective with a large message size of 128 megabytes. Now you can see that's roughly 94% of our maximum throughput that we can achieve on a real communication collective. And the same is true for broadcast. This is a true broadcast collective amongst all the nodes, and we're able to achieve 147 gigabytes per second. Last point about the communication collectives is on latency and message size. So here again, we've benchmarked all reduce. On the table on the left, we've benchmarked all reduce on a very small message size of 2 kilobytes so that the operation is completely latency dominant. The bandwidth is almost 0 in order to perform this operation. And you can see with 2 cards, we have a 3 microsecond latency between the 2 cards. And that's true end-to-end latency from when the instruction gets received to when it's completed. And you can see that it scales pretty linearly when you go from 2 cards to 32 cards. The table on the right shows our all reduced bandwidth with respect to message size. So you can see, as I talked before, we need about 128 megabytes to achieve the full maximum bandwidth on our links. But you can also see that even at a message size of as small as 8 megabytes, we're achieving roughly 70% or so of our maximum throughput. And so why do we care about low latency and small transfer size? Low latency and small transfer size enable efficient use of model and kernel parallelism. And that unlocks a lot of the limits that we have today on model size, because with data parallelism, you still need to contain the model on a single card, as well as the activations. But model and kernel parallelism unblocks some of this. It also enables a finer level of granularity with all reduce algorithms. So you can overlap more of the compute with communication, which again gives you higher utilization of the chip, since it's not blocked by communication. Thanks for the opportunity to speak today. I've been involved in the architecture and design of Crest since the very early days of Nirvana. And I've seen the program grow and mature these last few years at Intel. I'm really excited today that I've finally been able to disclose the architecture, and I'm looking forward to seeing these parts in customer hands in the near future.
We have a little time for audience questions, as before. Oh, go ahead, please.
Okay. Kiran Gunam from Western Digital. So great work. And one remark, though. I think one of the assumptions you're making is that the training workloads are going to be intensive. One of the questions I have is that, have you benchmarked your architecture for, let's say, MorphNet, in which you can do a lightweight training using an existing model for a new application, in which you have a structured sparsity? So essentially, the two questions are, have you benchmarked for MorphNet? The second question is that how well your architecture supports structured sparsity.
So we're still working on full workloads benchmarks, and we'll be releasing those later this year.
OK, thank you.
Dave Patterson, Berkeley, and Google. Yeah, you started off with peak performance as a misleading figure, and then you came back with micro benchmarks. Yep. So we look forward to you participating in MLPerf. Is the next deadline the target?
I can't comment on that at this time. We'll be releasing more data before the end of the year.
Yeah, at some point, if people don't release MLPerf results, it'll be suspicious.
Yep.
Andrew, if you have a moment, if I recall earlier on, Nirvana built FlexPoint, which was a different numerical approach, and you've since pivoted to bfloat 16. Could you tell us a little bit about the journey from one way of doing math to another?
Yeah. So we initially did FlexPoint on our first chip, and what we found was that it was difficult to scale out, not the chips, but to scale up all our software and the product with FlexPoint. So when there was more research going into numerics and we found bfloat, we decided to pivot to bfloat at that time.
Great answer. Thanks once again, Andrew. So for our next talk, I think it's my honor to introduce, among a field of really great hot chips, the hottest chip possibly ever presented at Hot Chips. I believe this is the first substantive public disclosure by Cerebras, and so it's kind of cool to see there, after being in stealth mode for so long, what they're up to. Our speaker today is Sean Lee, who is a co-founder and the chief of hardware architecture there. He has worked at MIT on transactional memory, at AMD on high-performance CPUs, at SeaMicro, a startup, doing server interconnects for hardware virtualization of, server interconnects and hardware virtualization of both network and storage. And he's going to tell us about their amazing new system.
Thanks, Cliff, for that introduction. As Cliff said, I'm Sean. I'm co-founder and chief hardware architect at Cerebras Systems. When we started Cerebras, we had a vision and a mission to drastically change the landscape of compute for AI. To achieve radical improvements, we knew we needed radical new technology. And over the last 3 years, we've been working tirelessly to bring that vision into reality. And today, I'm proud and excited to share with you what we've built. To solve the problem of deep learning compute, at Cerebras Systems, we have built the largest chip in the world. I have to figure out how to use this. And that's what it looks like. That's our chip. Thank you. That's our chip. That's a single piece of silicon. It's the biggest processor ever built. It's over 46,000 square millimeters. In that size, we have 1.2 trillion transistors powering 400,000 AI-optimized cores. The cores are fed by 18 gigabytes of super-fast on-chip memory with an unprecedented 9 petabytes per second of memory bandwidth. And all of it's connected with a 100 petabit per second on-chip fabric. Now, those are some really big numbers. But how big is this chip anyways? Well, it's really big. It's in fact the largest square we can carve out of a round 300 millimeter wafer. That's 215 millimeters by 215 millimeters square. That's 8.5 inches per side. This picture shows a scale comparison with a large max reticle chip today. The Cerebras wafer scale engine is 56 times larger than the largest GPU today. It's an enormous chip. That's pretty cool. But the question is, why does this make sense, and why now? The answer is deep learning. Deep learning is the most important computational workload of our time. It's proliferating across multiple industries, multiple applications. It's a large, growing portion of the data set in the data center, the workload in the data center, and it's growing at an insane rate. I don't need to tell you this. You guys all know this. However, deep learning training is hard. Both the size and the shape of the problem make it very challenging. The size of the problem is massive. We need billions to trillions of operations for every sample. And then we have to run millions to trillions of samples to train a neural network. You multiply those up, all of a sudden you're in the peta to exascale compute range. So you need a massive scale architecture. The shape of the problem is also very challenging to scale. At the fine grain, there's a lot of parallelism. That's really awesome because that presents a lot of opportunity to accelerate. However, at the coarse grain, the problem is very interesting. It's inherently a serial problem, right? That's because training is the process of applying small changes serially on the neural network. So the combination of the size and the shape of the problem make training neural networks really hard on today's architectures. So the question is, what does that look like today? Today, we use brute force parallelism. At the fine grain, we have dense vector processors, like GPUs. That works, but it's limited when the compute is not large, uniform blocks. At the coarse grain, we use existing scale-out technologies. We use interconnects like Ethernet, InfiniBand, or NVLink. And using today's technology, this allows us to run multiple instances of the neural network at a time. We call that data parallel. Now again, this works, but is limited because of the inherent serial nature of the problem. So the end result is you get scaling, but it's quite limited, and it's very costly. So the question is, can we do better? Specialized accelerators are the answer. Our industry has shown time and time again that special applications need special accelerators. DSPs for signal processing, switch chips for packet processing, and GPU chips for graphics. Now, for neural network processing, the question remains, what is the right architecture? An architecture optimized for deep learning has these 5 key properties. First, it starts with a core that is optimized for neural network primitives. Second, the core should have flexible and should be programmable because neural network architectures are still changing all the time. Third, it should handle sparse compute because neural networks have a lot of fine-grained sparsity. Memory should be local because neural network memories are all local and have low data reuse. And lastly, all of the cores should be connected with a fast interconnect because neural network layer-to-layer communication requires high bandwidth and low latency. So the foundation of any architecture is the core. A core optimized for deep learning has 2 key properties. One, it should be flexible. And that's because the neural network space is still evolving so fast. Researchers are coming up with new architectures all the time. Second is the core should handle tensor operations very efficiently at high performance. And that's because tensor operations are the core of all neural networks. They form the bulk of the compute of any neural network. And so our core is a fully programmable core with a set of general instructions used for control processing. These general instructions include standard things like arithmetic, logical, load store, branch, all the stuff that we're all used to for general purpose compute. On top of that flexible foundation, we then layer tensor operations that give us high performance data processing. Here in our core, tensor operands are first-class operands. And what do I mean by that? Here's an example of an fmac instruction that's operating on 3D and 2D tensors directly as first-class operands in the same way it would registers. This is our purpose-built, deep learning optimized core. When designing the core, one of the key properties we had to consider was sparsity. Deep learning has a lot of techniques like ReLU, like dropout, that introduce a lot of sparsity naturally into the neural network workload. If we designed a data path that ran the dense network on the left, when in fact the network looked like the sparse one on the right, that would be very wasteful. And so our core has native sparse processing in the hardware. This is done with data flow scheduling, where all the compute is triggered by the data. This allows the hardware to filter out all the sparse zeros, and we can skip all the unnecessary work. When we do this, we not only save the power and energy that would otherwise be wasted on the unnecessary work, we can skip past it and get performance and acceleration by moving on to the next useful work. And then all of this is enabled because our architecture has fine-grained execution data paths. It is built up of many, many small cores with independent instructions. And it is this property that lets us run efficiently on dynamic, fine-grained, and very non-uniform work. The next component of any architecture is memory. A memory optimized for deep learning should match the properties of neural network memory. Neural network memory is used for weights, it's used for activations, and it has very low reuse. And that's the reason why traditional memory architectures are not well optimized for deep learning. Traditional memory architectures are shared, they're slow, they're far away. We've had many talks today about exactly that problem. It requires a high degree of data reuse through caching to get performance. Unfortunately, the fundamental neural network operation is a matrix vector multiply. And matrix vector multiplies have very low data reuse. And so the community, all of us, to work around this problem, we run multiple parallel vectors. We call that mini-batch. That transforms that matrix vector multiply into a matrix-matrix multiply. And matrix-matrix multiplies have a lot of data reuse, caching techniques work. And in today's memory architectures, that lets us drive up utilization. However, it changes the learning dynamics, the training dynamics, and so isn't always desirable. And so our memory architecture is optimized for deep learning. It is fully distributed within the compute. It's all on-chip SRAM, where all the memory is right next to the core. The physics of driving tens of microns from memory to the data path is so much more efficient than going off-chip, and this is what enables us to get orders of magnitude higher memory bandwidth. This lets us get full performance running out of the memory. It lets us run the native matrix vector multiply at full performance, regardless of batch size. It allows the ML to be done the way the ML wants to be done. The last main component in any architecture is the interconnect. And here, a deep learning optimized interconnect should be high bandwidth, and it should be low latency. And it should factor in the local communication patterns of neural networks. And the reason for this is that all neural network communication is relatively local. Neural network layers talk from one layer to the next. Sometimes in more advanced topologies, you have skip layers or residual connections, those kind of things. But even then, the communication is relatively local. Our fabric is fast and fully configurable. It uses small, single-word, fine-grained messages. Everything is done in the hardware, so there's no software overhead. The topology is a 2D mesh, and that is extremely efficient for local communications that matches the neural networks. Here, it's this that allows us to get high bandwidth and low latency. But to achieve radical performance gains, training neural networks requires more compute than we can fit on a single die. We need more cores, we need more on-chip memory, we need more fabric bandwidth than we can fit on a single die. This is what we need. We need to build big chips. By building a wafer-scale chip, we can combine the massive compute, on-chip memory, and fast interconnect at a scale never seen before. It gives us cluster-scale performance on a single chip. That's because we have hundreds of thousands of cores. It lets us bring gigabytes of memory so that it's only one clock cycle away from the cores. That is impossible with off-chip memory. It lets us connect all these cores with a fully on-chip interconnect fabric that gives us orders of magnitude higher fabric performance than connecting many small chips together using existing technologies. And because the chip is so large, instead of running one layer at a time, you can map the entire neural network onto the chip at once. This lets us run model parallel, and you get linear performance scaling. Since there's only one instance of the neural network, you don't have to increase batch size to get cluster scale performance. And lastly, because it's one chip, we get all of it at vastly lower power and less space. To apply all the compute power of the wafer towards a single neural network problem at once, we co-designed our software with this architecture. The Cerebras software allows the neural network to be expressed in common ML frameworks like TensorFlow, like PyTorch. It extracts the neural network from the framework and performs placement and routing to map it to the compute fabric optimally. It does this by sizing the neural network layers based on compute, memory, and bandwidth needs. Larger layers get more resources. Just that simple. By doing this, we can apply all of the compute of the entire wafer towards a single neural network problem at once. This sounds pretty awesome, and it's easy, right? It turns out it's not that easy. It turns out building a wafer scale chip is pretty challenging. We had to rethink almost every aspect of chip design. A lot of what we in the chip design industry take for granted every day, a lot of it we had to rethink, we had to reinvent. We had to figure out how to connect all these die together to even build such a large thing. Then how do you yield an entire wafer? We had to design a package that could handle the thermal expansion of something this large. And then finally, even after all of this, how do you power and how do you cool this thing? So in the remainder of the talk, I will walk through these and talk through the solutions that we've came up with. The first challenge is connecting these die together. We start with independent die, but instead of cutting up all the die and making small chips, we cut out the largest square in that wafer. Standard fabrication processes has a space between the die called the scribe line. On top of the scribe line, we add wires to connect the die together in partnership with TSMC. This allows us to extend our 2D mesh fabric from within the die to adjacent die. You get the same connectivity between cores as you do between die all the way to the wafer scale. Here we're talking about driving less than 1 millimeter of distance on silicon, right? We don't even think about that normally because it's so easy. The physics of driving less than 1 millimeter on silicon is so much more efficient than going off chip through connectors, through PCBs, sometimes even through cables for traditional chip-to-chip interconnect. And it's this that gives us the full bandwidth, both at the die level all the way to the wafer scale. The next main challenge is yield, right? It's impossible to yield a full wafer with 0 defects. Yields are there, the defects are there even in mature processes. When it comes to yield, redundancy is your friend. We designed this architecture with small, uniform cores so that we could use redundancy to address yield at very low cost. The design includes redundant cores. It includes redundant fabric links. As you can see in the picture on the left, the active cores are the dark yellow ones at the bottom. The redundant ones are on top. When there's no defects, we don't use our redundant cores. On the right, when there's a defect, we use a redundant core to replace the defective core. And then we reconnect the fabric using the redundant fabric links. By using this technique, we can drive yields incredibly high, and it's all transparent to software because software sees a fully uniform fabric. The next major challenge is thermal expansion. As you can see in the picture, we have silicon on top, we have PCB on the bottom. Silicon and PCB, unfortunately, expand at very different rates under temperature. If we use traditional package technology, there simply would just be too much mechanical stress because of the size of the wafer. Or put another way, it would just crack. So to solve this problem, we developed a custom connector. This connector bridges the silicon directly to the PCB, and it's specially designed with features to absorb the variation while maintaining connectivity. As you can see, the largest variation occurs at the edges because of the lateral expansion. Now there's a question of how do you package this thing, right? No traditional packages exist. Our package includes the PCB, the connector, the silicon, and the cold plate. All of these components need to be held together with precise alignment. So here, we developed all custom packaging tools and processes. We have custom machines, we have custom processes to ensure alignment, to ensure that we have special handling for this large unit, and ultimately to hold the entire thing together. Here are some photos from our package assembly. The last challenge is power and cooling. The concentrated high density of current and heat are simply too high for traditional methods. As you can see in the picture, traditionally, power is distributed laterally in power planes through the PCB. Unfortunately, there simply isn't enough copper in the PCB to do it that way. If we did, we would only be powering the edges of the wafer. Similarly, the traditional way of cooling is to run cool air over top of the chip. And again, the concentrated high density of heat is too high for that to be effective. If we did that, we would only be cooling the edges of the wafer. The solution here is to use the third dimension. Here, we bring current directly through the PCB directly into the wafer, perpendicular to the wafer, as you can see in the diagram. Similarly, for cooling, we bring cold water into the cold plate, and then we bring the heat out directly perpendicular to the wafer. Now, by using these techniques, we can power, we can cool the entire wafer uniformly, both at the edges and in the middle. So now I've described the power, the cooling, and the various other challenges to building the Cerebras wafer scale engine. These problems are really hard, but by solving it, we built the largest chip in the world. It gets cluster scale performance to solve today's hardest deep learning problems, and it does it all on a single chip. And it's not just a picture, it's real. I have one to show you guys here today. You know, I still get a kick out of looking at this thing. Somebody earlier in the conference told me that in an audience with all engineers, a baseball probably isn't the best reference. But hopefully this gives you an idea. So finally, I just want to say that we have this working. We have it running customer workloads. And if you guys are as excited about this as we are, please stay tuned in the coming months for more information. Thank you very much.
Bravo, Sean. That was awesome. I suspect we have a few questions. Maybe on the left?
Okay, this is Kiran again from Western Digital. It's a great work. I have one question.
Yeah.
When do you expect to show that as part of an actual working demo system?
So today we are talking mostly about the chip and some of the physical challenges that we had. Over the coming months, we'll be disclosing more about the overall system and application, end-to-end performance and all that.
Got it, got it. So one more question. So can you design a round chip? Let's say if you have, so that you don't need to waste whatever the periphery you're cutting.
It's funny, we get that question all the time. Why is it square? The main reason is for convenience within the system. And it gives us souvenirs to take home.
Okay. So and also one more question. So
Yeah.
I have just one more question. So you know, like AMD and Intel sell like 2 processor systems, 3 core systems, 4 core systems. Actually, they make 8 core systems. Sometimes because of the yield issues, they sell different number of cores in the processor. So how do you sell your one, like half square, like a quarter square? Like how do you, like when you have yield issues?
Yeah, so it turns out that, especially on relatively mature processes, that yield is actually fairly uniform, especially when you start looking at entire wafers. And so we pretty much don't need to worry about. I think you're talking about are we going to be binning our wafers, right? Like this one has fewer cores versus another. That's not something that we believe we need to do.
Got it, got it.
Okay,
So
one brief question per person because of the size of the lines, please. Yep, right side.
One question. This is a fantastic achievement, but is it economically viable? I mean, does it cost less than a house in Silicon Valley?
So that's a great question. I think one of the most challenging things, obviously, here is that you got to keep the costs low. But one of the things that makes it structurally, easier to do that is everything is amortized across that entire wafer, right? And so if you think about it, right, I mentioned it's 56 times larger than a single chip. It's almost like you have a 56x margin that you can play with in terms of all of the design overhead.
Do you have a regular processor, von Neumann architecture processor to do the housekeeping work?
All of our processors are regular processors.
I mean,
as in they can all run, as I mentioned, they can all run general purpose code.
And that's a fully synchronous chip. How do you handle the EMI for thousands, hundreds of thousands of a processor?
So we let everything drift. It's not fully synchronous.
Oh, okay. Thank you.
So, can I ask? So my name is Dan. I'm a bit confused. I don't think it will fit into my pocket. And actually, I'm coming from a period where we called it pattern recognition rather than machine learning. I guess machine learning is more sexy. But my question is really, the training is generally not the most critical pass in terms of timing, generally. Sometimes you can afford days, definitely milliseconds. So can you, and what's more important is, of course, to put it in the system and continue to learn. So can you give me an example, that will convince me that all of this is nice, but also useful?
So I think the main problem here is, it may be true that sometimes you can wait days or weeks, to let a training run complete, because then you can basically, now you have their trained model, right? But I think if you talk to any of the people doing any of this work, it's never that simple, right? Training state-of-the-art neural networks can take days, weeks, or even months. And this is an experimental science often. And so you need to do it over and over and over. And so this is the reason why training is so important right now, right? I'm not even talking about just from a Cerebras point of view, but in this whole industry, is because it is causing all of us to have to, iterate at a very, very low pace, right? When was the last time that we programmed anything where we had to wait days or weeks to verify if the code was correct, right? And that's what we're seeing across the industry, and that's why we and many others are looking at innovative solutions here, because we really need a massive jump in terms of performance to get to the experience that we all want as software and application engineers.
Let me make this the last question in the interest of time, and I hope Sean will be around after the talks.
I will definitely be around.
Excellent. So that side, please.
Yeah. What's the clock rate?
So we're currently not disclosing any of our performance data yet. That's the reason why clock rate was missing from there. But like I said earlier, stay tuned. In the coming months, we'll be disclosing application performance as well as system information.
Sure. Thanks.
Let's thank Sean one more time. So if you've been to our booth area outside, you might have noticed the Habana demo, where they're showing off both their inference and training real hardware, at least some of which is available to buy right now. So product you can actually ship a PO for. Our speaker is Eitan Medina. He's going to round out this training session and talk about the Gaudi training architecture that Habana has built. He's their chief business officer, and he's a little bit bashful about the business officer title, and maybe point out that he's also been VP of Engineering at Audience, VP of Engineering and Consumer Products at Cavium, VP of Cellular Engineering at Marvel, and CTO of Galileo. So expect an excellent technical talk from him.
Okay, thank you, Cliff. So as part of this talk, we'll walk through the architecture requirements from our inference and training processor, walk through the inference processor, which is simpler, go to Gaudi, and then talk about our approach to scale out with Gaudi. So if you look at requirements from a processor, actually AI is not different from any other processor. Almost any application will tell you that they want to see performance, power efficiency, programmability, and cost. So if you want to more seriously dive into inference and training processor, we need to look at the specific metrics that influence our definition. So a training processor needs to converge to a target accuracy within the shortest time possible. That's obviously the main metric, but it also correlates to throughput somewhat. With inference, you care about the throughput of getting the actual results, and some applications care about the latency as well. In terms of memory capacity, while the forward propagation path is similar between inference and training, with training you actually need to retain results in order to do the back propagation path, so that tends to influence the memory capacity to require a much larger memory. With inference, the memory requirements are relatively medium. You need to just compute throughout the model to get the result. Scale-out is probably the area where the biggest differences exist, because to shorten training time, like the previous speaker pointed out, we end up using many processors trying to scale by distributing the load. So I'll talk about how that influences. With inference, you don't see that as much. Typically, most of the available processors contain the full model, or you maybe in some cases you split it and do some moderate scaling in the single digits. Data types is a very heavy area of research, always trying to reduce it. Right now, with training, we see floats as the dominant data type. With inference, trading off accuracy and throughput, some application can live with lower accuracy, so we see integer more dominant, or mixed precision actually is the most dominant. So what do we do at Habana? Habana is a company focused on data center and cloud. We started with our inference processor, which is available on the left, called Goya. And just recently, we introduced our training solution. So for us as a company, since inference laid out the groundwork for training and it's simpler, let's have a look into the inference architecture first. So Goya processor is actually a heterogeneous architecture. It's composed of 3 main engines. The engines are TPC, you've heard this name before, a Tensor processor core. It's a TPC cluster of just 8 processors. A GEMM engine, which is a highly configurable engine, and DMAs that need to move data around. And you typically want to have all 3 work concurrently as much as you can to get the maximum performance out of it. So as we started with the clean sheet architecture, it's really important for us to custom design our VLIW SIMD core to be really optimal for the type of compute that you need ultimate flexibility, full programmability. So this Tensor processor core will accelerate nonlinear functions, provide GEMM acceleration, tensor addressing, latency hiding, and multiple other capabilities that need to be fully programmable at the hands of the programmer. Working together with the GEMM operation engine that, as the name said, is really a matrix math engine, highly configurable engine. And using resources that would allow the processor generally to fully contain most of the topologies people would use on a single processor. The processor would support mixed precision, and this mixed precision would allow us to put in the hands of the user the control of what to use at compile time. So for quantization, we really want to make sure that the accuracy loss tolerance that differs between applications really can be served by giving the hooks during compile time to the user in how to make this trade-off. There is a coarse grain control, and there's even a fine grain control down to the tensor level. Going next is to really go and show you the actual precision results of the complete toolchain on various topologies. In this example, you can see a ResNet 50 example where quantizing to a mixed precision that is dominant with 8-bit integer result in just a 0.4% accuracy loss. And if you really insist on no difference to the reference FP32 trained model, you would probably use a 16-bit. If you really want to search for that tumor in an X-ray, 0.4% is probably too much for you. But in general, inference is an engine that we designed it so that for different application, different workload, you can select which quantization strategy you'd want to use. The software stack that comes with Goya is even more important than the processor itself. Habana as a company really comes with a deep background in DSP and CPU, so we see ourselves more as a software company that does hardware for a living. And as such, the software stack is composed to give the user the ability to get full programmability on one hand, but also a high degree of customization that sometimes is required. So on the left side, you see the compile time tools. At the heart of the software stack is a graph compiler that has a built-in quantization engine. That compile time software generates what we call a recipe, which is an execution plan. That execution plan can be used by the runtime under the user control, and multiple recipes can be loaded down to the targeted hardware. What you see here in the bottom right is the actual Goya card, which includes our processor and DRAM that can host many recipes, and runtime can schedule execution those. Now, if we look into the software stack has an API of either a C API or a Python. We can ingest topologies directly from neural network frameworks, exchange formats, and machine learning compiler by interpreting the Python code, or you can feed it using a C API. The process involves providing us with example data together with the topology, such that after we create the internal representation of the topology, we also go through a quantization process. And during that flow, the graph compiler would discover the resident kernel libraries that exist. Habana provides a very rich kernel library, but we also made sure to provide our customer the ability to create their own kernels, so that if they created custom layers, they can easily match it with custom kernels of their own. So, we could talk all day long about architecture, but at the end, you probably want to see results. So this graph would be familiar to many. We shown ResNet 50 results 11 months ago. 11 months later, Goya is still the performance leader by a considerable margin versus existing solutions. And the unique thing about Goya is that this achievement is not rooted in very advanced process node. We use a modest 16 nanometer. But really with architecture, what you see here is 15,000 images per second on the ResNet 50 V1.5, the same one that MLPerf uses, while at the same time giving you 1 millisecond latency. So with the ground-up design architecture, you suddenly get both high throughput and low latency at the same time. Vision is not all, right? We get asked a lot, what about other things? So today, we're really happy to share with you results for one of the most advanced, arguably the best-in-class natural language understanding model. BERT allows reuse across many tasks by building a model that built based on transformers and really introduce bidirectionality to the context that you get for different words. If you look at Goya architecture, we were able to map BERT to the hardware. All operators are supported by the hardware we have inside Goya. The GEMM and TPC are actually fully utilized. And we see that the instruction set in the TPC is able to accelerate many of the nonlinear operations. And we designed this chip long before BERT was invented. So the point here is to show you how the Goya architecture can map to support applications from different worlds. We were able to achieve also a very high degree of accuracy by using a combination of IN16 for GEMM operations and using FP32 for some of the nonlinear operations like layer normalization. So we feel it's a very good example representing the versatility of Goya. And the actual performance is demonstrated outside. If you come to see the demo, you can see the task Squad 1.1 is used as a data set. You can see that Goya outperforms a leading GPU in throughput and also supports under 10 millisecond latency for real-time applications. So now that we covered Goya, and I want to stress that we intend to submit in the next available window for MLPerf some of the MLPerf benchmarks. That's really coming soon. Now let's go into Gaudi. So what were the goals going into Gaudi? In terms of performance, we really want to focus on performance at scale, because after all, for most users, you need to scale your system in order to accelerate the training. So high throughput at low batch size was a key requirement we focused on, along, of course, with high power efficiency. The other big decision we took several years ago, actually, is to make Ethernet work for scaling AI. We really thought as a startup, if we were going to come to the field, if we are able to make Ethernet work for inter-processor communication efficiently, then this will bring a lot of advantages to our customer. First and foremost, to avoid any proprietary interface, allow them to have freedom of choice of suppliers by not polluting their infrastructure with proprietary interface. And secondly, obviously, they enjoy an ecosystem of suppliers that can allow them to have choices and flexibility. So what we'll do next is go over the Gaudi architecture and then talk about scaling. Now, if you look at this block diagram for Gaudi, it actually looks very similar to Goya, and that's not by chance. Gaudi also has a TPC, GEMM engine, and DMAs. It has one big addition, which is the networking interface that I mentioned. Gaudi integrates 10 ports of 100 gigabit Ethernet interfaces powered by Rocky V2 engines integrated together with the compute engine. The memory architecture includes 32 gigabytes of HBM. As I mentioned, you need much more memory. And the evolution of our design and addressing new data types resulted in additional features in the GEMM engine as well as the TPC. Gaudi supports also bifloat 16 and some additional capabilities in the instruction set. So in terms of software architecture, there are some additions to the software stack that you've seen before. First and foremost, we expose what we call Habana communication library, which is basically exposing primitives for allowing inter-processor communication to be controlled by the host, a thing like gather, broadcast, reduce, etc. Gaudi also supports just-in-time and ahead-of-time compilation so that we can support things like dynamic shapes. The architecture is a multi-stream architecture, so think of exposing to the software both compute as well as communication stream, ability to chain them, etc. So if you look at Gaudi today, Gaudi is the only AI processor that actually integrated Rocky RDMA on chip. So next I'll talk on what's the value, what can you do with that. 10 ports of 100 gigabit Ethernet running Rocky V2 is pretty incredible networking interface on chip. But we are not the first one that pointed out to the potential of Rocky to really improve the ROI for customers who buy more and more servers and expect to get better scaling. What you see here is a quote by NVIDIA CEO that pointed out that Rocky as a protocol could really help improve the ROI on scaling AI. So naturally, we should compare how does it work. First, for those of you who are not familiar with Rocky, Rocky origin started with InfiniBand, and Rocky is simply, in one sentence, taking the InfiniBand payload and encapsulating over Ethernet IP UDP header. So you basically get the advantage of RDMA running on standard Ethernet networking. So if we look at the Gaudi solution versus existing solutions that you can get today, on the left side, you can see the NVIDIA plus Mellanox solution. The NVIDIA GPU has an NVLink interface, but to get networking scale-out, it needs to connect to an InfiniBand NIC, providing today one port of 100 gigabit Ethernet. The Gaudi solution basically integrates compute and networking and providing you 10x the throughput of Rocky V2. The architecture allowed us to completely offload the inter-Gaudi communication during the training. And typically what you see this type of processor would be to exchange parameter tensors, subtensors. Accordingly, Gaudi supports both linear write as well as tensor write to each other. And to support the quality of service, we've put the hooks into the silicon to support congestion avoidance and congestion control mechanisms. We support both lossy and lossless fabrics. And from our standpoint, making Ethernet work means that you make the edge, the endpoints smarter so that you can use off-the-shelf Ethernet switches to allow this to scale. So the hardware that we provide, you can come and see at the table outside. We provide mezzanine cards that are OCP OEM form factor. And we also offer to our customers an option to buy an HLS1 system, which is an 8-Gaudi system utilizing these OCP OEM cards. Of course, they can design their own as well. So if you look inside HLS1, what we chose to do in order to enable our customers to design as modular system as possible is to integrate 8 of the Gaudi processors and simply provide connectivity to the box. You do not see here CPU integrated, and that's intentional because we figured that we want to let our customer choose the CPU to acceleration ratio and the type of CPU they want. So you can use 4 ports of 4 connectors of mini SAS HD to connect CPU to the box. You can choose 1-to-1, 1-to-8, anything in between. And you are using the Ethernet connectivity to interconnect the processor internally in a point-to-point links with a non-blocking full mesh connectivity. So out of each processor that has 10 ports, 7 are going to the others, and 3 are available for scaling up. So you get 24 ports of 100 gig as a networking interface. So to build a full rack, right, what you would do is take an accelerator box like HLS1. Of course, you can buy HLS1 or you can design your own, and choose the CPU that fits your application, connect it over PCIe, and that's your basic unit. And to scale further, you simply select Ethernet switch from your favorite vendor and connect Ethernet cables, and you're done. So let's compare the Gaudi-based box solution, the HLS1, to other solutions that exist today. If we compare to the DGX, what you see is that unlike the DGX architecture, which is using NVLink inside the box, with Gaudi, we are using a standard Ethernet communication to connect those devices to each other. The connectivity inside HLS1 is non-blocking, all-to-all, and we provide much higher networking uplink connectivity, 24 ports instead of 4 ports in the case of DGX1 or 8 in the case of DGX2. And another subtle difference that is actually pretty meaningful is that unlike the DGX architecture, we do not force you to share the PCIe bandwidth between scale-up and host interface. So PCIe is fully dedicated to host traffic, and we provide the option to separate scaling to Ethernet. The RDMA engine inside Gaudi can actually talk also over PCI, but we figure that separating the two would give a yet additional advantage in terms of performance. HLS1 is, and OEM is not the only form factor. If you step outside, you'll see our dual slot PCI card. To provide an option for network scaling, you see 2 QSFP-DD connectors on this card, so up to 800 gigabit Rocky V2 are available for scaling. And you could fit it into existing server and hook up the cards to each other using basically any topology. It could be daisy chain together, or you can even stack up those servers using Ethernet switch, same as you've seen before. So let's explore some training topologies and see what can you do with this type of connectivity. So naturally, the most common one is data parallel, but we'll talk also about model parallel. With data parallel, you basically take the training data set and divide it across all the processors that you have. Every processor holds the entire model, and the processors need to exchange the updates based on the data that each of them learn to each other. They don't need to share activation. So if you employ hierarchical reduction of the gradients, you enjoy this attribute where you can do hierarchical, the reduction allows you to execute the learning while not requiring the same amount of bandwidth as you go up the stack. So you can employ a scheme of hierarchical switching connectivity while still getting the full throughput of training across all these processors. Of course, conditioned with your processor being able to handle small batch size. So that ties the link to what I mentioned before. The goal was high throughput at small batch size, so you can do data parallel efficiently. So you can build a system as large as you want, from a single processor to 8 to thousands, using commonly available networking infrastructure that exists in every data center. You don't need to train your technicians on some new interface technology, certainly nothing proprietary. It's all Ethernet. So that's a data parallel to you. Model parallel is more involved in terms of communication. When the model is too big, or if you choose to split your model across processors, the processor needs also to exchange activations with each other. That could be truly huge bandwidth. Now, the fact that we integrated such a huge networking bandwidth on each processor reveals another advantage that you could utilize from Gaudi. And that is to build solutions that expose all this bandwidth outside. So on the diagram you see here below, you see 8 processors, but instead of having some of the links interconnected inside the box, you could expose all ports to the box interface. So in this case, you could build a box that is actually the same size, that exposes 80 ports of 100 gigabit Ethernet through QSFP-DD connectors. And this will allow you to do model parallel at full bandwidth with solutions that are much larger than the biggest solutions today, right? DGX2 has 16 GPUs inside, lots of bandwidth inside the box, but very limited connectivity to the outside. By using Gaudi-based acceleration boxes and Ethernet switches that you deploy in parallel, you can interconnect all those boxes in a non-blocking fashion at full throughput. So that opened the possibility of solving much bigger model parallel training problems. So if you look at the Gaudi architecture and hardware solutions, why would you consider using it? I would summarize it in 2 reasons. One is the core architecture, the heterogeneous architecture, providing you high throughput at low batch size, gives you higher throughput, which is the potential of accelerating your training, boosting your productivity, and reducing power. And the thing that may be even more important to some customers is finally you have a processor vendor that doesn't force you to use a proprietary interface in scaling the architecture. So avoiding a proprietary lock-in from any processor vendor is really important. And having access to Ethernet, which is, has no competition almost in terms of ecosystem support, right, is a pretty good combination in our opinion. Thank you.
Thank you, Eitan. That was cool. We have a little bit of time for questions if people want to ask.
So I heard the word quantization processor. So I wonder, what do you do for quantization that requires a processor? What type of quantization do you do?
The quantization doesn't require a processor. What I described is that within the software stack that we provide with the inference processor, we have a quantization engine that allows the user to choose whether to quantize how aggressively.
But is it linear quantization?
It's taking your neural network model that is typically trained in FP32, and then quantize the model either completely or by tensor to data types that are efficient, more efficient in terms of power and compute, and gives you the feedback on what's the accuracy. Okay. I'm not sure. Do you understand my answer?
No. I mean, I just asked if it's linear. It sounds like it is linear, but we can talk.
Quantization
offline.
is typically done from floating point to integer.
And if you go from float to integers, then you have dynamic problem, like what do you do if it doesn't fit? But we can take it offline.
Okay.
Because you said quantization, and I'm into quantization.
Okay.
Yeah. Algar Akanyan from Cognify. I noticed that on your block diagram, you have your GEMM engine way on the top.
Yeah.
It's isolated. What kind of NOC do you use? What kind
This is a logical diagram, so don't take it as a floor plan.
So it is distributed. Can you comment on interconnectivity, on-die interconnectivity?
So it is one functional unit in the die.
Okay, thank you.
Michael Shea from UC Berkeley Extension. The question I have is, this is an excellent talk about a solution for data center. What is the minimal viable solution for edge gateway in the IoT application?
You can use a single processor. The question is what's the power envelope you have, right? And what's the type of server this will get inserted to. So if you have a server that has a dual slot PCI port, then Gaudi can fit there.
Oh, that's nice. I'll talk to you offline.
Okay.
Thank you.
Thank you, Eitan.
Thank you.
So that brings to a close the ML training session and our first day of technical discussion. I'd like to thank all the speakers for incredible breadth and depth and ambition in what was presented today.